Tonight, we are going to explore one of the most quietly unsettling ideas in all of modern cosmology. Not unsettling in a way that disturbs rest, but in the way a long-held assumption, once gently questioned, begins to feel uncertain in ways it never did before. The universe, as best as science can determine, has no center. It never did. And the reasons for this are not hidden inside some obscure corner of theoretical physics. They are woven into the nature of space itself, into the way the cosmos expands, and into the limits of what any observer anywhere can ever truly know about where they stand in relation to everything else. We will move through this idea slowly. We will begin with why the question of a center feels so natural to ask, and why the intuition behind it has remained so persistent throughout human history. We will explore how our understanding of the universe changed over centuries, and what those changes revealed about the assumptions we had quietly been carrying all along. And from there, we will move outward into the geometry of an expanding universe, the strange behavior of light and distance across cosmic scales, and what it truly means to live inside something that has no edge, no boundary, and no fixed point that any observer could honestly call the middle of everything. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. There is something worth acknowledging at the start. The question of where the center is feels like a reasonable one. It feels like the kind of question that should have a straightforward answer. When we look up at the night sky, we see stars distributed in every direction. When we consider that the universe began from an extremely hot and dense state nearly 14 billion years ago, it seems natural to imagine that explosion having a location, a point in space from which everything rushed outward. And if everything rushed outward from a single point, then surely that point is the center. This reasoning is intuitive. It is also, as we will see over the course of this evening, built on a misunderstanding of what the Big Bang actually was, and what space itself actually is. Chapter 1. The Instinct for a Center. Human beings have always placed themselves near the middle of things. This is not a flaw in our thinking. It is, in many ways, a natural consequence of how perception works. We each experience the world from a fixed vantage point. Everything we see, hear, and sense radiates outward from where we stand. The horizon is always equidistant in every direction. The sky arches equally above us whether we face north or south. There is a deep, embodied sense that we are located at the center of the space we inhabit. And for most of human history, that feeling was extended outward to the cosmos itself. The earliest models of the universe were geocentric. Earth sat at the middle, and the stars and planets moved around it in careful, ordered paths. This was not simply a failure of imagination. It was a logical conclusion drawn from the available evidence. The ground does not appear to move. The sun rises and sets. The stars trace arcs across the sky each night. Everything in the observable heavens appeared to orbit around the place where the observer stood. Placing Earth at the center of the cosmos was, in a very real sense, the most straightforward reading of what the senses reported. The shift away from that model was slow and, for those living through it, deeply disorienting. When Nicholas Copernicus proposed in the 16th century that Earth moved around the Sun rather than the other way around, he was not simply offering a more accurate description of planetary motion. He was beginning the long process of removing the human observer from the privileged position at the center of everything. The Sun became the center. Earth became one planet among several, tracing a path around a star that was itself unremarkable. But even that was not the end of the displacement. As telescopes improved and the scale of the cosmos became clearer, it became apparent that the Sun was not at the center of the galaxy either. Our star sits in one of the spiral arms of the Milky Way, roughly 26,000 light-years from the galactic core, a thoroughly ordinary position in a thoroughly ordinary region of a galaxy that contains several 100 billion other stars, and then the galaxies themselves. When astronomers in the early 20th century established that the faint smudges visible in long exposure photographs were not clouds of gas within the Milky Way, but entire galaxies, vast collections of hundreds of billions of stars lying at enormous distances. The scale of the universe expanded again, suddenly and dramatically. The Milky Way, which had seemed immense, became one galaxy among what we now estimate to be hundreds of billions of others, distributed across a cosmos so large that the numbers involved lose their meaning if held too tightly. Each of these expansions in our understanding carried with it the same quiet message. The place where we happen to stand is not special. The vantage point from which we observe the universe does not correspond to any privileged position within it. And yet, the instinct persists. Even knowing all of this, the mind still reaches for a center. It still wants to know where the middle is. That instinct is worth sitting with rather than dismissing. It points towards something real about how we experience space. It is just that the universe, it turns out, does not share our preference for having a middle. Chapter 2. What the Big Bang actually was. Of all the misconceptions that feed the intuition for a center, the most persistent is the image of the Big Bang as an explosion. The word itself encourages this. An explosion is something that happens at a place. It originates at a point, releases energy outward in all directions, and leaves behind a pattern of debris that, if you traced it carefully enough, would lead you back to the spot where it began. If the universe began with something like an explosion, then the center of the universe ought to be the place where that explosion occurred. But the Big Bang was not an explosion in space. It was an expansion of space itself. This distinction is not a minor technical clarification. It changes everything about how the origin of the universe should be imagined. In an ordinary explosion, there is a location. There is a before and an after, and there is a surrounding space into which the force releases itself. The explosion happens within an existing environment. The Big Bang had no surrounding environment. There was no pre-existing space waiting to receive the expanding matter and energy. Space itself, along with time, matter, and energy, came into being as part of the event. There was no container. There was no outside. There was no location in a prior space from which the expansion began. This is genuinely difficult to visualize, and that difficulty is worth acknowledging rather than glossing over. Our minds are shaped by experience of the everyday world, where things happen in places, and places exist within a larger space that surrounds them. The concept of space itself beginning, of there being no larger context in which that beginning occurred, sits outside the kind of thinking that daily experience prepares us for. One way to approach it is to consider what the word everywhere meant at the moment the universe came into being. In the very earliest moments, the entire observable universe, everything that would eventually become hundreds of billions of galaxies, was compressed into a region of extraordinary density and temperature. But that compressed region was not sitting inside a larger, emptier space. It was all there was. Every point in that early universe was touching every other point. And as space expanded, it did not expand into anything. It simply expanded. Every point moved away from every other point, not because things were flying through space away from a central location, but because the space between all points was growing. This is the heart of the matter. The expansion of the universe is not the movement of galaxies through space. It is the stretching of space itself, carrying galaxies along with it, the way dots drawn on the surface of a balloon move apart from one another as the balloon is inflated. No dot is at the center of the balloon's surface. Every dot moves away from every other dot as the surface expands. And from the perspective of any single dot, all the others appear to be receding, which can create the impression that the dot doing the observing must be at the center of the expansion. This balloon analogy has its limits, as all analogies do. The surface of a balloon is two-dimensional, and we are tempted to imagine the center of the expansion as being located at the center of the balloon itself, a point in a third dimension that the two-dimensional surface does not contain. The universe is not like this. There is no higher dimension in which a true center sits just out of our reach. The expansion happens within the dimensions that exist, and it happens everywhere simultaneously, with no privileged origin point. Georges Lemaitre, the Belgian priest and physicist who first proposed what would become the Big Bang theory in the 1920s, described the early universe as a primeval atom, a single extraordinarily compressed state from which everything emerged. His thinking was rooted in the mathematics of general relativity, and it led him to the conclusion that the universe had a beginning in time. But the geometry of that beginning, as the mathematics made clear, was not the geometry of an explosion with a center. It was the geometry of a space that was simultaneously everywhere at once, dense and hot throughout, with no special location and no outer boundary. Edwin Hubble's observations, published in 1929, provided the observational confirmation that the universe was indeed expanding, that galaxies were receding from us, and that the more distant a galaxy was, the faster it appeared to be moving away. This was the evidence that, traced backward in time, pointed toward a past state of extreme compression. But Hubble's data also showed something else. The recession was not concentrated in one direction. It was happening in every direction equally. Every galaxy, regardless of where it sat in the sky, was moving away. This is exactly what would be expected if space itself were expanding uniformly. And it is entirely inconsistent with the picture of an explosion that originated at a single point. The Big Bang, then, was not a moment that happened somewhere. It was a moment that happened everywhere. And because it happened everywhere, it left no location behind that could serve as a center. The question of where the Big Bang occurred has a straightforward answer. It occurred at every point in the universe simultaneously, including the point where you are sitting right now. Chapter 3. The Geometry of an Expanding Universe. To understand why the universe has no center, it helps to think carefully about geometry. Not the geometry of shapes drawn on a flat page, but the geometry of space itself, and the ways in which space can be curved, finite, or infinite, without any of those properties requiring a center or an edge. In everyday experience, space feels flat. Parallel lines stay parallel. The angles of a triangle add up to 180 degrees. The shortest path between 2 points is a straight line. This is the geometry that Euclid described, and it matches the world we move through closely enough that for most practical purposes it serves perfectly well. But flat Euclidean geometry is not the only kind of geometry that is mathematically consistent, and it is not necessarily the geometry that describes the universe at the largest scales. Consider the surface of a sphere. On that surface, the rules of geometry change. Two lines that begin parallel, say, two lines of longitude drawn straight up from the equator, will eventually meet at the poles. A triangle drawn on the surface of a sphere has angles that add up to more than 180 degrees, and crucially, the surface of a sphere has no edge and no center. You can travel in any direction on the surface of a sphere indefinitely without ever reaching a boundary, and there is no point on the surface that is more central than any other. The center of the sphere exists in three-dimensional space, but it is not on the surface itself. For a two-dimensional being living on the surface, no center exists within their world. Now extend this thinking to 3 dimensions. Just as a two-dimensional surface can be curved into the shape of a sphere, finite in area but without edges or a center on its surface, a three-dimensional space can be curved in analogous ways. A three-dimensional universe could, in principle, be curved so that traveling in a straight line in any direction would eventually bring you back to where you started, just as traveling in a straight line along the surface of the Earth eventually returns you to your starting point. Such a universe would be finite in volume, but would have no boundary and no center within the 3 dimensions that exist within it. Whether the actual universe is curved in this way, or whether it is flat and infinite, or whether it takes some other geometric form entirely, is a question that cosmologists have worked to answer through careful observation. The most precise measurements available, drawn from the detailed mapping of the cosmic microwave background radiation, the faint afterglow of heat left over from the early universe, suggest that the universe is geometrically flat, or very close to it, to the limits of what current instruments can detect. A flat universe, if it extends infinitely in all directions, also has no center. In an infinite flat space, every point is equally central and equally peripheral at the same time, because those concepts lose their meaning when there is no boundary to be central relative to. You cannot be closer to the middle of something that has no edge. The idea of a center requires the existence of an outer limit from which the middle can be measured, and an infinite space has no such limit. This is one of the places where the intuition built from everyday experience begins to quietly fail. We are accustomed to objects that have centers because we are accustomed to objects that have edges. A circle has a center because it has a circumference. A room has a center because it has walls. Remove the boundary and the center dissolves with it. There is a third possibility worth considering. The universe might be finite in volume but still have no center, depending on its topology, the way its overall shape connects with itself. A three-dimensional space could, in principle, be arranged so that it loops back on itself in complex ways, the way the surface of a donut does in 2 dimensions. Such a space would be finite without having a boundary, and it would have no center in any meaningful geometric sense. The honest answer, given current knowledge, is that the precise global geometry and topology of the universe remains uncertain. The observable universe, the region from which light has had time to reach us in the roughly 13.8 billion years since the Big Bang, is finite and bounded, not because space ends there, but because light has not had time to travel from beyond that boundary. What lies beyond the observable universe, whether space continues infinitely or curves back on itself, is not something that current observations can determine. But within any of these geometric possibilities, a flat infinite universe, a positively curved finite universe, a universe with complex topology, none contains a center in the way our intuitions expect. The geometry simply does not support one. And this is not a gap in our knowledge waiting to be filled. It is a consequence of the structure of space itself, as best as the mathematics of general relativity and the observations of modern cosmology allow us to understand it. Space, it turns out, is far stranger and far more interesting than a simple container with a middle and edges. It is a dynamic, curved, expanding medium whose geometry is shaped by the matter and energy within it, and whose overall form may be one that human intuition, built for navigating a small and local world, was never quite designed to picture clearly. Chapter 4. The Expanding Flow of Space. One of the most important pieces of observational evidence bearing on the question of a center comes from watching how galaxies move, or more precisely, from watching how galaxies appear to move, because the distinction between actual motion through space and the apparent motion caused by the expansion of space is one of the most illuminating in all of cosmology. When Edwin Hubble and his colleague Milton Humason compiled their measurements of galaxy distances and recession velocities in the late 1920s, the pattern that emerged was clean and striking. Galaxies were moving away from us, not just a few of them, and not just in one direction. All of them, distributed across the sky, were receding, and the relationship between distance and recession speed followed a remarkably simple rule. The farther away a galaxy was, the faster it appeared to be moving away. This relationship is now known as the Hubble law, and the constant that describes the rate of expansion is called the Hubble constant. The immediate temptation, looking at this data, is to conclude that we must be at the center of the expansion. Everything is moving away from us. We appear to be the fixed point around which the universe is retreating. It would seem to follow logically that our position is somehow special, that the Milky Way sits at the origin point of the outward rush. But this conclusion dissolves the moment you consider what the same observations would look like from a different galaxy. Imagine an observer located in a galaxy several 100 million light-years away from us. From their vantage point, they would see exactly the same thing we see. Every galaxy in their sky would be receding from them. The more distant a galaxy, the faster its recession. They would have exactly as much reason to conclude that they were at the center of the expansion as we do, which is to say, the appearance of centrality tells us nothing about actual position. This is the defining characteristic of a uniform expansion. In a space that is stretching equally in all directions at all points, every observer sees every other point receding. There is no location that is genuinely stationary, while everything else moves away from it. The recession is not a property of any particular place. It is a property of the expanding space between all places. A useful way to think about this is to return to the balloon analogy from the previous chapter, and to be more specific about what the dots on the surface experience. Place 3 dots on the surface of a balloon. Call them A, B, and C. As the balloon inflates, each dot moves away from the other two. From dot A's perspective, dot B and dot C are both receding. From dot B's perspective, dot A and dot C are both receding. From dot C's perspective, the same is true. No dot is stationary. No dot is the center. The recession is mutual and symmetric, and it arises entirely from the stretching of the surface rather than from any dot moving through the surface. Now add a rule. The farther apart two dots are, the faster they appear to move apart, because there is more surface between them that is stretching. This is precisely the Hubble law. The proportionality between distance and recession speed is not a sign that the observer is at a special location. It is a mathematical consequence of uniform expansion. It would hold true from any vantage point in the universe. The region of the universe within which this recession pattern is observed is sometimes called the Hubble flow, the large-scale motion of galaxies carried along by the expansion of space. Individual galaxies do have their own peculiar velocities, small motions through space caused by gravitational interactions with their neighbors. The Milky Way and the Andromeda Galaxy, for instance, are actually approaching each other, drawn together by mutual gravity despite the general expansion. But on the larger scales, where the gravitational influence of individual structures becomes negligible compared to the overall expansion, the Hubble flow dominates, and the pattern of universal recession holds with remarkable consistency. What the Hubble flow reveals, when examined carefully, is that the universe has no preferred direction and no preferred location for an observer. The technical term for this is homogeneity and isotropy, properties that describe a universe that looks the same in all directions and from all positions, at least when averaged over sufficiently large scales. A homogeneous and isotropic universe is, by definition, a universe without a center, because a center would be a special location that broke the symmetry. The cosmological principle, as it is known, holds that the universe is homogeneous and isotropic on large scales. This is not simply an assumption. It is supported by observations of the distribution of galaxies across the sky, by the extraordinary uniformity of the cosmic microwave background radiation, and by the consistency of the Hubble flow in every direction we have been able to measure. The universe, as far as observation reaches, looks the same regardless of which way we point our telescopes. And that sameness is itself the evidence that no direction is special, and therefore no location is central. There is something quietly reassuring in this, even as it dismantles a comforting intuition. The recession of all galaxies from our position is not a sign that we are at the center of something. It is a sign that we are participants in something, a vast, uniform, ongoing expansion in which every point shares equally in the experience of watching everything else move away. Chapter 5. The Ancient Light That Fills All Space. If there is a single piece of observational evidence that speaks most directly to the question of whether the universe has a center, it is the cosmic microwave background radiation. This faint, cold glow of light, the oldest light in the universe, released when the cosmos was only about 380,000 years old, fills the sky uniformly in every direction, and its properties tell us something profound about the nature of the early universe and the space it occupied. To understand what the cosmic microwave background is, it helps to picture the universe as it existed in its earliest stages. In the first hundreds of thousands of years after the Big Bang, the universe was filled with a plasma, a hot, dense mixture of electrons and atomic nuclei so energetically agitated that light could not travel freely through it. Photons, the particles of light, were constantly scattered by the free electrons, unable to move more than a short distance before being redirected. The universe was opaque in the way that a thick fog is opaque, not because there was no light, but because the light could not travel in a straight line long enough to carry information from one place to another. As the universe expanded, it cooled. After roughly 380,000 years, the temperature dropped to the point where electrons could combine with atomic nuclei to form neutral atoms, primarily hydrogen and helium. This moment is called recombination, though the name is slightly misleading since the electrons and nuclei were combining for the first time rather than reuniting. With neutral atoms formed and free electrons no longer available to scatter photons, the universe became transparent. Light was suddenly free to travel unimpeded across space. The photons released at that moment have been traveling ever since. In the nearly 14 billion years that have passed, the expansion of the universe has stretched their wavelengths enormously, shifting them from the infrared into the microwave portion of the electromagnetic spectrum. Today, they arrive at our detectors from every direction in the sky, carrying an image of the universe as it appeared at the moment of recombination. The earliest picture of the cosmos that light itself can provide. What those photons show is a universe that was, at recombination, extraordinarily uniform. The temperature of the cosmic microwave background varies across the sky by only about 1 part in 100,000. In every direction we look, the early universe had essentially the same temperature, the same density, and the same conditions. The tiny variations that do exist, the 1 in 100,000 fluctuations, are the seeds from which all the structure in the universe eventually grew. The slight overdensities that gravity would later amplify into galaxies, galaxy clusters, and the vast cosmic web of filaments and voids that characterizes the large-scale structure of the universe today. But the overall uniformity is the dominant feature. This uniformity is deeply significant for the question of a center. If the universe had expanded from a single point in a pre-existing space, we would expect to see evidence of that origin, some asymmetry, some direction in which the early universe was denser or hotter, some gradient pointing back toward the place where it all began. We see none of this. The cosmic microwave background is isotropic, to a degree that is, by any measure, extraordinary. It is the same in every direction, from every position we have been able to observe. The COBE satellite, launched in 1989, provided the first precise full-sky map of the cosmic microwave background and confirmed its remarkable uniformity. Subsequent missions, including the WMAP satellite in the early 2000s and the Planck satellite, which completed its observations in 2013, produced increasingly detailed maps that revealed the fine structure of those tiny temperature fluctuations with extraordinary precision. Each of these maps told the same story, a universe that, at its earliest observable moment, was smooth and uniform in all directions, with no preferred axis, no hotter pole, and no colder void pointing toward an origin. There is a subtlety worth noting here. The cosmic microwave background does show one large-scale pattern that initially seems to violate this uniformity, a slight temperature difference between one hemisphere of the sky and the other, sometimes called the dipole anisotropy. But this is not a feature of the early universe. It is caused by the motion of our own galaxy through space, which Doppler shifts the background radiation slightly warmer in the direction we are moving toward, and slightly cooler in the direction we are moving away from. Once this motion is accounted for and subtracted from the data, the remaining background is uniform to the 1 in 100,000 level described above. The cosmic microwave background, then, is not merely a beautiful relic of the early universe. It is a detailed record of the conditions that prevailed everywhere in the cosmos at a moment when the universe was less than 400,000 years old. And what it records is a universe without a special place, without a hot center and a cool periphery, without any geometric feature that would allow an observer to point in one direction and say, that is where it began. Every direction leads to the same age, the same temperature, the same early conditions. The early universe surrounded every point equally, and a universe that surrounds every point equally is a universe that has no center at all. Chapter 6. What any observer sees from anywhere. There is a particular kind of vertigo that comes from sitting with the idea of an infinite universe. Not the sharp vertigo of sudden disorientation, but a slower, quieter kind. The feeling that arrives when the mind genuinely attempts to hold the concept of something that has no boundary, no edge, and no outside. It is the kind of feeling that is worth staying with for a moment, because it points towards something real about the nature of space and the nature of observation. And it has direct bearing on why the question of a center is not merely unanswered, but unanswerable in any meaningful sense. Every observer in the universe, regardless of where they are located, is surrounded by a sphere of space from which light has had time to reach them. This sphere is called the observable universe, and its size is determined by the age of the universe and the speed of light. Since the universe is approximately 13.8 billion years old, and since light travels at a fixed speed, the most distant objects whose light can have reached us are those from which light set out roughly 13.8 billion years ago. The boundary of the observable universe is not a wall or an edge in space. It is a horizon, a limit defined by time and light speed, rather than by any physical boundary. Beyond that horizon, space almost certainly continues. The universe does not end at the edge of what we can see. It simply becomes inaccessible to observation from our current position, because light from those regions has not yet had time to reach us. In an expanding universe, some of those regions are receding so quickly that their light will never reach us. They are, in a practical sense, permanently beyond our horizon. But their existence is not in doubt. They are simply elsewhere in the same continuous space. Now consider what this means for the concept of a center. Every observer in the universe has their own observable universe, their own sphere of accessible space centered on their position. An observer in a galaxy 10 billion light-years from the Milky Way has an observable universe centered on their location, overlapping with ours but extending in directions we cannot see. Their horizon is their own. Their sphere of accessible space is unique to them, as ours is unique to us. In this sense, every observer is at the center of their own observable universe. This is not a metaphor. It is a geometric fact. The observable universe is, by definition, centered on the observer, because it is defined by what that observer can see. But this personal centrality is entirely a product of the observation process itself. It tells us nothing about whether the observer occupies a special position in the larger, unobservable universe that extends beyond their horizon. This distinction between being at the center of your observable universe and being at the center of the universe itself is one of the most important in cosmology. The two are frequently conflated, and the conflation is understandable, because for most of human history, the observable universe and the universe itself were assumed to be the same thing. The stars visible to the naked eye were thought to be all there was. Later, the Milky Way was thought to be the full extent of the cosmos. Each expansion of the observable horizon was accompanied by the same quiet realization. There is more beyond what we can currently see. The current observable universe extends roughly 46 billion light-years in every direction from Earth. This number is larger than 13.8 billion light-years because the universe has been expanding during the time that the light has been traveling. The sources of the oldest light we can detect have moved much farther away since they emitted it. But even 46 billion light-years in every direction is, in all likelihood, a small fraction of the total extent of space. Current estimates, based on the geometry implied by the flatness of the universe and the uniformity of the cosmic microwave background, suggest that the total universe is vastly larger than the observable portion, possibly by many orders of magnitude, possibly infinite. In an infinite universe, the concept of a center becomes not just absent, but logically incoherent. A center is a point equidistant from all boundaries. An infinite space has no boundaries. Therefore, it has no center. This is not a gap in our knowledge. It is a consequence of the definition of infinity itself applied to space. Every point in an infinite universe is equally central, which is the same as saying no point is central at all. There is a philosophical dimension to this that is worth pausing on. The experience of being an observer, of standing somewhere and looking outward, creates an unavoidable sense of being located at the center of what is visible. The horizon curves equally away from us in all directions. The background radiation arrives with equal intensity from every point in the sky. The galaxies recede from us symmetrically. Every sensory and instrumental signal we receive is centered on our position, because we are the ones receiving it. This observer-centered perspective is built into the very act of looking, but the universe is indifferent to where we happen to be standing. The same horizon, the same recession, the same background glow would greet any observer anywhere in the cosmos. The centrality we experience is the centrality of awareness itself, not the centrality of location. We are at the center of our experience, as every conscious observer must be. We are not at the center of space. Chapter 7. The End of the Special Observer. There is a principle that sits quietly at the foundation of modern cosmology, rarely stated explicitly in everyday conversation, but present in almost every assumption that scientists make when they study the large-scale structure of the universe. It is called the Copernican principle, named for the astronomer whose work began the long process of removing Earth from the center of the cosmos. In its modern form, the principle states something deceptively simple. We do not occupy a special place in the universe. Our position is ordinary. Our vantage point is typical. The conditions we observe from where we stand are not unique to us, but are broadly representative of what any observer, located anywhere in the cosmos, would find. This principle is not an established law in the way that the conservation of energy is a law. It cannot be proven from first principles, and it cannot be directly verified by observation, since we cannot travel to a distant galaxy and check whether the view from there matches our expectations. It is, rather, a working assumption, one that has proven extraordinarily productive, that is supported by every observation we have been able to make, and that becomes more compelling the more carefully the universe is examined. But it is worth understanding what it claims and why it matters, because it is one of the most powerful arguments against the existence of a cosmic center. If we did occupy a special place, if the Milky Way happened to sit at or near the true center of the universe, then the universe would look different from here than it would from elsewhere. There would be some observable asymmetry, some gradient in the distribution of matter or the temperature of the background radiation, some directional signal that pointed toward our privileged location. We would be able to detect in principle that we were somewhere particular rather than somewhere generic. No such signal has been found. Every survey of the large-scale distribution of galaxies has confirmed that matter is distributed with the same statistical properties in every direction. Every measurement of the cosmic microwave background has confirmed that the early universe was uniform across the sky. Every test of the Hubble flow has confirmed that galaxies recede from us with the same rate in all directions. The universe, as far as observation can reach, is consistent with us being located at a completely ordinary position, one of countless such positions, each of which would yield essentially the same view. The Copernican principle has been extended and refined over the decades since Copernicus first displaced Earth from the center of the solar system. Each extension has carried the same implication. The Sun is not at the center of the galaxy. The Milky Way is not at the center of its local group of galaxies. The local group is not at the center of the Virgo supercluster. The Virgo supercluster, now understood to be part of a larger structure called Laniakea, a vast supercluster spanning roughly 500 million light-years, is not at the center of anything larger that we have been able to identify. At every scale, our location appears to be unremarkable, embedded within structures that have no special orientation relative to the rest of the cosmos. This progressive displacement is sometimes described as the Copernican revolution continuing to unfold. Each time we have mapped a larger portion of the universe, we have found ourselves in the middle of it, not because we are at a special location, but because we can only see what is within our horizon, and our horizon is always centered on us. We have never found evidence that our position within that horizon is anything other than ordinary. It is worth considering what it would mean if the Copernican principle were wrong, if we did in fact occupy a special location. This possibility, sometimes called the Ptolemaic alternative in reference to the geocentric model that Copernicus displaced, has been taken seriously by a small number of cosmologists as a possible explanation for certain puzzling observations. Some of the apparent anomalies in the large-scale structure of the universe, subtle alignments in the cosmic microwave background, unexpected clustering patterns in galaxy surveys, have been proposed as potential evidence that our location is not as typical as the Copernican principle assumes. These suggestions remain highly controversial and are not accepted by the mainstream of the field. The evidence for large-scale homogeneity and isotropy is, on balance, overwhelmingly strong, but the fact that such proposals exist is a reminder that the Copernican principle, for all its explanatory power, is ultimately an empirical claim about the universe rather than a mathematical certainty. It is the best supported hypothesis available, and it leads directly to the conclusion that the universe has no center. But it rests, finally, on the accumulation of evidence rather than on logical necessity alone. What makes the Copernican principle so compelling, beyond the observational support it has received, is the alternative it displaces. To believe that we occupy a special location, that out of the hundreds of billions of galaxies distributed across hundreds of billions of light-years, the Milky Way happens to sit at or near the true geometric center of everything, would require an extraordinary coincidence. It would mean that the one location in the universe capable of asking the question of where the center is happened to be located at the center. The improbability of this is not a proof that it is wrong, but it is a very strong reason to look carefully at the evidence before accepting it. And the evidence, examined carefully, points consistently in the other direction. We are not at the center. We are not near the center. There is, as best as science can determine, no center to be near. Chapter 8. The largest structure with no center. If you could step outside the universe and look at it from a distance, which is of course impossible, but useful as a thought experiment, what you would see would not be a uniform fog of matter distributed evenly in all directions. You would see something far more intricate and far more beautiful. Matter in the universe is not spread smoothly through space like cream stirred into coffee. It is gathered into an elaborate three-dimensional structure. A vast network of filaments, sheets, clusters, and voids that cosmologists call the cosmic web. And the cosmic web, for all its complexity and for all the drama of its structures, is itself a powerful argument against the existence of a center. The cosmic web is the largest known structure in the universe. It is not a single object in the way that a galaxy or a star cluster is a single object. It is a pattern, a repeating, self-similar arrangement of matter that appears, as far as surveys of the universe have been able to reach, to continue in all directions without a special region of greater density or complexity that could be identified as a center or a hub. Understanding how this structure formed and what it tells us about the distribution of matter in the cosmos adds a layer of texture to the picture of a centerless universe that the earlier chapters have been building. The story of the cosmic web begins in the earliest moments of the universe, with the tiny fluctuations in density that were imprinted on space during a period called inflation, an extraordinarily rapid expansion that is thought to have occurred in a fraction of a second after the Big Bang. During inflation, quantum fluctuations in the energy field driving the expansion were stretched to cosmic scales, seeding the universe with regions that were very slightly denser than average and regions that were very slightly less dense. These fluctuations were tiny, the 1 in 100,000 variations recorded in the cosmic microwave background. But they were the seeds from which all subsequent structure grew. Over the billions of years that followed, gravity worked on these slight variations with patience and consistency. Regions that were slightly denser than average attracted more matter from their surroundings, growing denser still. Regions that were slightly less dense lost matter to their neighbors, growing emptier. This process, playing out simultaneously across the entire volume of the observable universe, produced the intricate filamentary structure that we observe today, a structure in which most of the matter in the universe is concentrated into thin sheets and elongated filaments, with vast, nearly empty regions called voids occupying the spaces between them. The filaments of the cosmic web are not narrow threads in the everyday sense. Each filament is typically tens of millions of light years in length and several million light years in width. Structures so large that the entire Milky Way, with its diameter of roughly 100,000 light years, would fit within one many times over. Along these filaments, galaxies are distributed like beads on a string, drawn together by gravity and connected by streams of gas that flow along the filament toward the dense nodes where filaments intersect. At the intersections of filaments sit the largest gravitationally bound structures in the universe, galaxy clusters and superclusters. These are collections of hundreds or thousands of galaxies, bound together by gravity and embedded within vast halos of dark matter that are invisible to direct observation but detectable through their gravitational effects. The largest of these structures, superclusters spanning hundreds of millions of light years, are themselves connected into the filamentary network of the cosmic web, strung between the enormous empty voids that occupy the majority of the universe's volume. Those voids deserve particular attention. A cosmic void is not simply an empty patch of space. It is a region that has been actively evacuated of matter by the same gravitational dynamics that built the filaments and clusters. As overdense regions grew denser by attracting matter from their surroundings, the regions between them grew emptier. Today, the largest voids in the universe span several 100 million light years, volumes of space so large that they dwarf the structures within the filaments, and yet contain only a small fraction of the matter that an equally sized region of average density would hold. The universe, by volume, is mostly empty, a foam of vast voids separated by the thin walls and filaments where matter has congregated. The largest known void, sometimes called the Boötes void, after the constellation in whose direction it lies, spans roughly 330 million light years. Within a region of that size, in a part of the universe with average matter density, one would expect to find thousands of galaxies. The Boötes void contains only a handful. It is not a special feature. Other voids of comparable scale have been identified in surveys of the large-scale structure. but it gives a sense of how dramatically matter has been redistributed from its originally smooth distribution into the concentrated filamentary network of the cosmic web. What is striking about the cosmic web, from the perspective of the question we have been exploring throughout this evening, is its statistical uniformity across the sky. The filaments, clusters, and voids are not concentrated in one region of the observable universe and absent in another. They are distributed with the same statistical properties in every direction, at every distance that surveys have been able to reach. The cosmic web looks the same, in a statistical sense, whether you map it in the direction of the North Galactic Pole or the South, toward the Great Wall of Galaxies that lies in the direction of the constellation Coma, or toward the equally impressive structures that surveys have found in the opposite direction. This statistical uniformity is exactly what the cosmological principle predicts. A universe that is homogeneous and isotropic on large scales will, when structure forms through gravitational instability, produce a web-like pattern that has the same statistical character everywhere. The particular arrangement of filaments and voids will differ from region to region, just as the particular arrangement of clouds in the sky differs from one part of the horizon to another. But the overall properties of the distribution will be the same. There is no region of the cosmic web that is structurally unique, no hub from which all filaments radiate, no central cluster that anchors the pattern. Several of the largest structures identified in surveys of the cosmic web have at various times been described in terms that imply a kind of superlative status. The largest known structure, the most massive supercluster, the deepest void. The Sloan Great Wall, identified in data from the Sloan Digital Sky Survey in 2003, stretches roughly 1.4 billion light-years and was for a time the largest known structure in the universe. The Hercules Corona Borealis Great Wall, identified in 2013, is larger still, a concentration of gamma-ray bursts suggesting a structure that may span up to 10 billion light-years, though its status as a gravitationally bound structure rather than a statistical fluctuation remains a subject of discussion among cosmologists. These superlative structures are genuinely impressive, but their impressiveness is a matter of scale rather than of position. None of them occupies a central location in the universe. None of them is the hub around which smaller structures are arranged. They are features of the cosmic web, large features, remarkable features, but features embedded within a pattern that continues, as far as surveys can determine, in all directions without a special region that anchors or organizes the whole. The cosmic web is, in this sense, a structure that expresses the centerlessness of the universe at the largest scales that structure itself reaches. It is a pattern generated by gravity acting on the initial conditions left by inflation, conditions that were themselves uniform across the observable universe, seeded by quantum fluctuations that had no preferred location and no special axis. The web that grew from those seeds inherited their symmetry. It is intricate and beautiful and almost incomprehensibly vast, and it is arranged around no center, oriented toward no hub, anchored to no fixed point in a space that contains no fixed points at all. To look at a map of the cosmic web, the kind of three-dimensional map that surveys like the Sloan Digital Sky Survey and its successors have made possible, is to see the universe at the scale where its true character becomes visible. The filaments and voids, the clusters and walls, the vast empty regions punctuated by bright concentrations of galaxies, all of it distributed across a volume so large that the individual galaxies within it are invisible at the scale required to show the whole pattern, and distributed, always, without a center. The map has edges because the survey has limits. The universe does not. Chapter 9. Dark Energy and the Accelerating Universe. There is a layer to the story of the expanding universe that adds considerable depth to the picture we have been building, and that bears directly on the question of whether any location in the cosmos could be considered special. It concerns the rate at which the universe is expanding, and the discovery, made in the final years of the 20th century, that this rate is not slowing down as gravity pulls matter together, but accelerating. The universe is expanding faster and faster with each passing epoch, driven by a form of energy whose nature remains one of the most profound unsolved problems in all of physics. The discovery came from observations of a particular type of stellar explosion called a Type 1a supernova. These explosions occur in binary star systems, where one star, a dense remnant called a white dwarf, accumulates material from its companion until it reaches a critical mass and detonates in a thermonuclear explosion of remarkable consistency. Because Type 1a supernovae always detonate at approximately the same mass threshold, they release approximately the same amount of energy each time, making them useful as what astronomers call standard candles, objects whose intrinsic brightness is known, so that their apparent brightness in the sky can be used to calculate how far away they are. In the late 1990s, two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, were using Type 1a supernova to measure the expansion rate of the universe at different epochs in cosmic history. The expectation, based on the understanding that gravity should be slowing the expansion over time, was that distant supernovae, which represent the universe as it was billions of years ago, would appear slightly brighter than a universe expanding at a constant rate would predict, because the expansion should have been faster in the past and slower now. Instead, both teams found the opposite. Distant supernovae were dimmer than expected, meaning they were farther away than a decelerating expansion would place them. The expansion of the universe was not slowing down, it was speeding up. This result, for which the leaders of both teams were awarded the Nobel Prize in Physics in 2011, was deeply unexpected and remains deeply puzzling. The accelerating expansion requires a source of energy that acts in opposition to gravity, something that does not clump together the way matter does, but instead permeates space uniformly and drives it to expand at an ever-increasing rate. This energy has been given the name dark energy, a label that conveys more about our ignorance than our understanding. We do not know what dark energy is. We do not know why it has the value it has. We know it exists because its effects are measurable, and we know it constitutes roughly 68% of the total energy content of the universe, the single largest component of the cosmos, outweighing ordinary matter and dark matter combined. The simplest mathematical description of dark energy treats it as a property of space itself, an energy density that is constant throughout the universe and does not dilute as space expands. This interpretation corresponds to what Einstein called the cosmological constant, a term he introduced into his equations of general relativity and later described as his greatest blunder, before the supernova observations rehabilitated the concept decades after his death. If dark energy is indeed a constant property of space, then it is, by definition, uniform. It does not vary from place to place. It does not concentrate in some regions and thin out in others. It is the same everywhere, filling every cubic meter of space with exactly the same energy density regardless of what else is present. This uniformity of dark energy is directly relevant to the question of a center, an energy that is constant throughout space, that drives expansion equally at every point and in every direction, cannot define a special location. It cannot create a region where expansion is faster or slower, denser or more diffuse, hotter or cooler than anywhere else. A universe pervaded by a uniform dark energy is, by virtue of that uniformity, a universe without a preferred place. The accelerating expansion driven by dark energy also has consequences for the long-term future of the universe that are worth considering in this context. As expansion accelerates, the distances between galaxies that are not gravitationally bound to one another grow at an ever-increasing rate. Eventually, on timescales vastly longer than the current age of the universe, galaxies beyond our local group will recede so quickly that their light will no longer be able to reach us. The observable universe will shrink. Future observers, if any exist, will find themselves in a cosmos that appears to contain only their own local group of galaxies, surrounded by an apparently empty darkness. They will have no way of knowing, from observation alone, that the vast structure of the universe beyond their shrinking horizon exists at all. This future contraction of the observable horizon is a striking reminder that the observable universe is not the same as the universe itself. What we can see is bounded by time, light speed, and the rate of expansion. The universe extends far beyond that boundary today, and in the future the boundary will draw closer rather than farther. The center of the observable universe will always be wherever the observer happens to be. But the observable universe is a window, not the whole room. Understanding dark energy also deepens the strangeness of the expansion itself. The space between galaxies is not just stretching passively. It is being actively driven apart by an energy that fills it uniformly. Every cubic meter of empty space contains this energy. Every region of the cosmos participates equally in the acceleration. There is no location that is exempt from dark energy's influence, and no location where that influence is stronger or weaker than anywhere else. The expansion it drives is as centerless as the space it inhabits, a force without an origin point, pressing outward everywhere simultaneously, indifferent to the positions of the galaxies it separates and the observers who watch from within them. The universe accelerates in all directions from all points. It has been doing so for roughly 5 billion years, since dark energy began to dominate over the gravitational pull of matter as space grew large and matter grew dilute. And in all that time, in all that acceleration, no center has emerged. None could. The physics of a uniform energy in an expanding space does not permit one. Chapter 10. Living without a center. There is a particular quality to the understanding we have been building through this evening, a quality that is different from the kind of understanding that comes from learning a fact or memorizing a figure. The absence of a center in the universe is not a piece of information that slots neatly into an existing framework. It is an idea that, if held long enough and seriously enough, quietly reorganizes the framework itself. It changes not just what we know about the universe, but how we relate to the space we inhabit and the position we occupy within it. For most of human history, the cosmos was understood in terms of hierarchy and location. There was a center, and things were arranged around it in order of their importance or their proximity to the divine. The geocentric model was not merely an astronomical claim. It was a statement about meaning, about the significance of the place where human beings lived, and the relationship between that place and the larger order of things. When Copernicus displaced Earth from the center, and when subsequent centuries of astronomy continued that displacement outward through the solar system, the galaxy, and the large-scale structure of the universe, Something more than a scientific model was being revised. A whole way of understanding human significance in relation to the cosmos was being quietly dismantled and replaced with something more austere and, in its own way, more honest. The universe that modern cosmology describes is one in which no location is special. The Milky Way sits in an unremarkable region of an unremarkable galaxy cluster, embedded within a supercluster that is itself one of many distributed across a cosmos that extends in all directions without preference or privilege. The conditions we experience here, the particular mix of matter and energy, the age of the stars in our neighborhood, the temperature of the cosmic background that surrounds us, are not unique to our position. They are broadly representative of what any observer in a broadly similar region of the universe would find. We are, in the deepest sense that cosmology can establish, typical. This typicality is worth sitting with. It is sometimes experienced as a kind of diminishment, a reduction of human significance to something negligible in the face of an indifferent and centerless cosmos. But there is another way to hold it, one that doesn't require diminishment and doesn't pretend to a centrality that the evidence does not support. The universe has no center, which means that every point within it is equally valid as a place to be. There is no location that is more fundamentally situated than any other, no vantage point that has a better claim to being the true middle of things. In the absence of a center, every position becomes, in a quiet way, as good as any other. The observer standing in the Milky Way, looking out at a universe that expands equally in all directions, is not at the center of the cosmos, but neither is anyone else. The galaxy 10 billion light years away, whose light reaches our telescopes after a journey longer than the Earth has existed, is no closer to the center than we are. The most distant quasar we have ever detected, blazing with the light of an active galactic nucleus in the early universe, occupies a position no more or less central than the chair you are sitting in right now. The universe distributes its space without favoritism, and every point within it shares equally in the condition of being somewhere without being the center. There is a philosophical tradition, traceable through many cultures and many centuries, that locates meaning not in position, but in awareness, not in where something is, but in the fact that it is capable of knowing where it is. The universe, as far as we know, does not experience itself. It expands without awareness. Its galaxies recede from one another without any of them noticing. The cosmic microwave background fills all of space with ancient light, but the space itself does not perceive it. It is only at certain points in this vast, centerless expanse, points where matter has organized itself into the particular complexity required for consciousness, that the universe becomes, in a sense, aware of its own existence. We are among those points. The awareness with which you follow these words, the curiosity that finds its way into questions about where the center of everything might be, the capacity to hold an idea and turn it over and find it strange. These are not common properties of matter. They are rare and remarkable, the product of billions of years of stellar evolution, planetary formation, biological complexity, and the long, slow development of minds capable of asking questions that the universe itself can ask. This does not make us central in any geometric sense. It does not restore the privileged position that Copernicus and his successors took away. But it does suggest that the question of significance and the question of centrality are not the same question, and that answering one in the negative does not automatically answer the other. The universe has no center. It is also, as far as we know, not conscious of itself anywhere except at the particular points where matter has become complex enough to wonder. Those points are not at the center of space, but they are where the universe looks back at itself. And that is something worth considering quietly before sleep. The displacement from the center of the cosmos, fully accepted and genuinely understood, does not leave us with nothing. It leaves us with a universe that is open in every direction, that extends without boundary or preference, that has no privileged point, and therefore no unprivileged one either. It leaves us in a space that is, in the most literal sense, equally available from wherever we happen to stand. And it leaves us with the particular, unrepeatable fact of being here, not at the center, but present, aware, and looking outward into a darkness that goes on without end in every direction at once. There is a gentleness to this. Once the initial disorientation passes, the universe does not require us to be at the center in order for us to be somewhere. And somewhere, in a cosmos this vast and this old and this indifferent to position, turns out to be enough. Chapter 11. A space without edges or origins. There is something fitting about arriving at the end of this exploration in the same spirit with which we began it. Not with a resolution, not with a neat conclusion that ties the question closed, but with a deeper familiarity with the strangeness of the space we inhabit. The universe has no center. It never did. And by now, having moved through the evidence and the reasoning that supports this understanding, the idea should feel less like an abstract scientific claim and more like a genuine property of the place where we find ourselves. A property worth sitting with quietly as the night deepens and the mind begins to release its grip on the day. We have covered considerable ground this evening. We began with the instinct for a center, the deep, embodied sense that we occupy a privileged position in the space we inhabit, a sense that served our ancestors well in navigating the local world, but that the cosmos, examined carefully, does not support. We trace the long history of displacement from the geocentric models of the ancient world through the Copernican revolution and the subsequent expansions of the known universe that pushed the Milky Way, the local group, and the supercluster into positions of increasing ordinariness. Each step in that history was a step away from the center, and the cumulative effect of all those steps is the picture that modern cosmology presents. A universe so large, so uniform, and so indifferent to position that the concept of a center simply has no place within it. We looked at the Big Bang and found that it was not an explosion at a location, but an expansion of space itself, an event that happened everywhere simultaneously, leaving no origin point and no direction that could be pointed to as the place where it all began. We examined the geometry of an expanding universe and found that whether space is infinite and flat or finite and curved, none of the geometries that observation supports contains a center in any meaningful sense. We watched the Hubble flow and saw that the recession of galaxies from our position is not evidence of our centrality, but evidence of a uniform expansion that would look identical from any vantage point in the cosmos. We studied the cosmic microwave background and found in its extraordinary uniformity a record of an early universe that was the same everywhere, in every direction, without gradient or asymmetry or any feature that would mark one location as the origin of everything else. We considered the nature of observation itself and found that the observable universe, the sphere of space from which light has had time to reach us, is centered on every observer equally, and that this personal centrality of observation is a property of awareness rather than a property of space. We examined the Copernican principle and found in it both a working assumption and a deeply supported empirical claim. that our position is ordinary, that the universe looks the same from any location at the larger scales, and that no special place exists from which the cosmos could be said to radiate outward. And we explored dark energy, the mysterious uniform force that is accelerating the expansion of space in every direction simultaneously, and found in its uniformity yet another expression of a cosmos that distributes its fundamental properties without preference or center. All of these threads lead to the same place, not a place in space, but a place in understanding, an acceptance that the universe is structured in a way that does not privilege any location, that does not arrange itself around a middle, and that does not provide any observer with a view from the center that another observer, located anywhere else in the cosmos, could not equally claim. This is, in one sense, a humbling conclusion. The history of cosmology is largely a history of humbling conclusions, a long series of revisions in which the universe turned out to be larger, older, and more indifferent to human position than the previous revision had suggested. Each revision required the adjustment of an assumption that had felt, before the revision, like simple common sense. Of course the sun moves around the earth. We can see it moving. Of course the Milky Way is the whole universe. The sky is full of its stars. Of course the universe has a center. Everything that exists must exist somewhere, and somewhere must be the middle. These assumptions felt natural because they were built from experience of the local world, where things do have centers, where positions do matter, where the middle of a room is a real and locatable place. The universe is not a room. It is not an object with an inside and an outside, a here and a there, a center and a periphery. It is the totality of space and time and matter and energy, a totality that contains every room, every object, every inside and outside, and that is not itself contained within anything larger. To ask where the center of the universe is to apply a concept that belongs to the world of objects to something that is not an object. It is to reach for a familiar tool in a situation where that tool does not fit. And yet, the reaching is understandable. The mind wants to locate itself. It wants to know where it stands in relation to the whole. This is not a failure of intelligence. It is an expression of the same curiosity that drives the inquiry in the first place. The desire to find the center is the desire to be oriented, to have a fixed point from which the rest of the map can be drawn. The universe, in declining to provide such a point, is not being unhelpful. It is simply being what it is, a space without a fixed reference, open in every direction, ancient beyond easy comprehension, and indifferent to the particular coordinates of the minds that try to understand it. What replaces the center, once it is genuinely relinquished, is something quieter and in some ways more interesting. It is the recognition that every point in the universe is equally a place to be. The space around you right now, the room, the darkness beyond the window, the air that carries these words, is not peripheral. It is not distant from the action. There is no action, no central drama unfolding somewhere else to which you are a remote audience. The universe is happening here, as fully and completely as it is happening anywhere. The expansion of space proceeds from this location, as it proceeds from every other. The ancient light of the cosmic microwave background surrounds this point as it surrounds all points. The dark energy that is slowly pulling the cosmos apart operates here with the same quiet persistence it brings to every cubic meter of space throughout the observable universe and beyond. You are not at the center, but you are not at the edge either. You are simply somewhere in a space that has no center and no edge, a space that is in every direction from where you lie, continuous and ancient and vast beyond the reach of any number that the waking mind can hold comfortably. There is rest in this. Once the disorientation fades, the universe does not require you to locate yourself relative to a center that does not exist. It does not ask you to measure your distance from an origin that was everywhere at once, and therefore cannot be pointed to from any direction. It simply continues, expanding slowly, cooling gradually, carrying its galaxies outward through a space that has no boundary and no middle. While the particular arrangement of matter that constitutes a conscious mind settles into stillness, releases the need to know exactly where in the infinite it happens to be, and rests. The cosmos is large beyond measure. It is old beyond easy imagining. It is structured in ways that resist the categories the everyday mind brings to it. And it has no center, not because something is missing, not because the question remains unanswered, but because the universe is precisely the kind of thing for which a center is not a meaningful concept. It is complete without one. It is whole without one. And on a quiet night, with the stars distributed equally in every direction above a dark and resting world, that wholeness is something that can be felt as well as understood. A vast, unhurried, centerless space, holding everything there is, going on in all directions at once, needing nothing more than it already has. If this was a good companion tonight, a like or a subscribe helps other curious minds find their way here.